Okay, so this is the kind of questions you're going to get, and we might do a little lab that involves this a little bit. Um, what can cause diffusion to go faster or slower? Well, since it's all about the movement of particles, right? Anything that makes the particles go faster, which is more energy, and we call that measurement again of the average speed of particles temperature. So in a hotter environment, diffusion is going to go faster, right? If we push them around, it'll go faster, pressure, right? And then something that doesn't have to do with their speed, but has to do with the rate of diffusion is the concentration gradient. The greater it is, the faster diffusion will occur. Here we go again with these diagrams. So if I asked you, here we have, we'll call this situation A, B, and C, right? In which of them is the rate of diffusion the fastest? Well, assuming that the temperature is the same for all of them, and you're not given any indication it's not, and the pressure, right, you would pick A. Why? Because the difference between one side and another is the greatest. The gradient is the steepest. That's another way we say that, right? Where is there no diffusion happening again? Here. The rate of diffusion here is 0. The rate of particle movement is some kind of rate. This has a temperature. They're moving. But again, there is not a net movement from higher concentration to lower because there is no place of higher concentration and lower. So another way to summarize all this is that diffusion requires a gradient. If there's no gradient, there's no diffusion by definition. Okay, so now this little thing, um, somebody dreamed up long ago as a good little device, this U-shaped tube, where in the middle of the U is a membrane, semi-permeable, right? This is also a very commonly used on a test kind of diagram to ask test questions about. So now we're going to switch though from the diffusion of particles like these dark ones here to the diffusion of the particles that they're dissolved in, right? Because water's a particle too. It's moving around at random, Brownian motion, right? Since it's a charged particle, it needs help to get through the membrane. And those proteins that help water molecules get through a membrane are appropriately called aquaporins. Okay, so that's facilitated diffusion of water, but for no especially good reason, somebody decided to give that its own special name, osmosis. Osmosis is only the diffusion of water, right? So it follows all the same rules. From a higher concentration of water to a lower concentration of water, that's osmosis, okay? So look at this situation, right? We have obviously a higher concentration of dissolved particles on the right side of this. The word we're going to see in the next slide for that is hypertonic. Hyper meaning more dissolved solute. The other solution in contrast is hypo. Hypo means less, hypotonic compared to this one, right? But look at this membrane. They made it, I know it's kind of small, but they made it so that you can see the spaces in between the dots, which kind of represent gaps in the cell membrane, are not big enough to let these solute particles through. The only thing that can pass through is water. So in this situation, what's the direction of diffusion of water going to be? What's the direction of osmosis going to be? Well, now we look at the concentration of water. If this area, we said, has a higher concentration of dissolved stuff compared to this area, it's got to have a lower concentration of water. There's only two things in a solution, the solvent and the solute. And if you've got a higher concentration of solute in one area, you must have a lower concentration of water. So where is there a higher concentration of water? Over here. So which way is water going to go? From higher water concentration to lower. Okay? You have to be careful with these words. So I'm going to practice them now and then a bunch of other times. All right? Hyper and hypotonic, those adjectives that describe a solution compared to another solution, are only used to describe the solute concentration. So we said this side is more concentrated with water, right? But we don't say it's hypertonic in terms of water. We just don't use hypertonic to describe the water situation. So, more practice with that. Here we go. Hypertonic, hypotonic always refer to solute concentration, and they're comparative. So, if we talk about solution A, right, and we say it's hypertonic, we have to be comparing it to some solution B somewhere, which if this one is hypertonic compared to that one, that means this is hypotonic compared to that one. It's always comparative. Okay? Now, if two solutions have equal concentrations of solute, we call them isotonic. Iso is the prefix that means the same. Hyper more, hypo less, iso the same, always referring to solute concentration. Okay? Now here's some stuff in red again. I really like this one, if you read that. Items referring to the role of the cell membrane, in transport in this case, may address hypotonic, hypertonic, and isotonic solutions. However, the assessment should be on processes, not terminology. What's that mean? I'm not sure. But I think what it means is that if they use these terms, they're going to like define them for you. I'm going to expect you to know what they mean, right? They want you to be able to predict which way things are going, right? In other words, I think they're not going to ask you the definition of these terms. But to communicate in general, you need to know definitions of words. So you're going to know these. Yes, yes. Okay, so now here we go. I'm going to pick one, okay? Based on its appearance, which of these two, we'll call this the left side and this the right side, which of these two is hypertonic compared to the other one? Well, this should be easy, right? Hypertonic means more, hyper more. More what? Dissolved particles. Well, this side's the only one that's got dissolved particles. So it's obviously hypertonic compared to that one. This is hypotonic compared to that one. Okay? How about this one down here? Hyper-hypo. Well, you know, it's kind of even, but it's not exactly even, right? If you look at it and count, you see we got 8 particles over here in this much space, and in the same amount of space we have 5, 7, we got 10 if you count them. So which one's got more solute concentration? This one. So again, the left side here is hypertonic compared to the right side. Okay. So now, let's talk again about osmosis. Let's go up to this one since I didn't scribble on it. If that was the setup, what's your prediction about the direction of osmosis in this system? Osmosis, you would predict, would be from right to left. Osmosis, again, is the movement of water. Where's there a higher concentration of water? Over here. Lower over here, right? So while the yellow particles might be diffusing from left to right, the direction of diffusion of the solute is from left to right. The direction of diffusion of the water is from right to left. In fact, if you stop and think about it, this should make sense to you. The overall direction of solute diffusion always has to be opposite to the direction of water diffusion. Because wherever there's a higher concentration of solute, there has to be a lower concentration of water. So the solute goes from where it's high to where it's low. The water goes from where it's high to where it's low. That should make sense. Most of the questions you get on a test are probably going to ask you what's the direction of the diffusion of water, of osmosis. They don't all have to be, but you need to read it carefully to make sure you're sure which one they're asking. Because the concept is simple. The net direction is always from a higher concentration to lower, no matter what kind of particle it is.